Hello, everyone, and welcome to our presentation on MPC 24-520, the assessment of safe work indicators in transportation construction using personal monitoring systems hosted by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University. TLN is a dynamic partnership with the four state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Center for Transformative Infrastructure Preservation and Sustainability, known as CTIPS, which was formerly known as MPC, which is where this research is coming from. This partnership allows us to deliver technical transfer, best practices, training, and research to the transportation industry. For more information, visit our website at translearning.org or ctips.org. We are joined today by Dr. Caroline Clevenger and Dr. Madi Ghafouri, and I will turn the presentation over to them to give their intros.
Hello, my name is Dr. Caroline Clevenger, and I'm a professor at the University of Colorado, Denver, and the director of the Construction Engineering and Management program. This research was funded by MPC, and actually as a precursor, we did some research with these personal monitoring systems to prove that they were meaningfully documenting differences in construction work. I then invited Madi, Dr. Ghafouri, to help with a research project that was very exciting because we were wondering, could these monitors be used to predict what was going to happen for construction workers? So I am going to hand it over to Dr. Ghafouri and let him present our results. It was an exciting project, and it was nice because we were able to document actual work on a bridge right downtown in Denver, Colorado. So I will hand it over now, and thank you, Dr. Ghafouri.
Hello, everybody. Thank you very much for joining us. Thank you, Dr. Clevenger, for the introduction. Without further ado, let's dive into the presentation. By the way, I forgot to introduce myself. I'm an assistant professor in the Department of Building Construction Science and Data Science at Mississippi State University. At the time that we were conducting this research, I was a PhD student in University of Colorado, Denver. So let's get started. So transportation construction projects usually involve physically demanding work, a lot of manual and labor work, including heavy lifting, long working hours, and this work is usually in hazardous environments. Based on the literature, 20% to 40% of construction workers exceed physiological thresholds. This is based on the literature review that we did. And physically demanding work can lead to fatigue, exhaustion, decreased quality of work, productivity, and ultimately more accidents and injuries. So right now we are trying to figure whether we can use PSM devices in order to monitor and help these construction workers in these hazardous environments. Physical status monitoring devices, or PSMs, can measure physiological metrics of construction workers in real time. And based on the literature, they have been shown potential for application on construction sites. According to the literature, heart rate specifically is a reliable indicator of physical demand and workload, and is widely used in physical demand measurements in the literature. Not only for construction, I'm talking about sports science, I'm talking about every area that involves human work. So heart rate is a good and reliable indicator of physical demand. Again, based on the literature, limited research exists on assessing physical demand in transportation construction with respect to physiological acceptable thresholds and boundaries. So the objectives of this research are these 5 objectives. We wanted to apply a non-intrusive system to monitor and assess the physical demand of transportation construction workers. We wanted to analyze variations in physical demand across different construction activities, specifically transportation construction activities. And we wanted to assess workers' heart rate against acceptable physiological thresholds that are established in the literature, and analyze physiological factors affecting heart rate and model and forecast the heart rate based on physical activity. And at the end, when we have done the analysis, we wanted to develop deep learning models to see whether we can forecast heart rate in advance. So these are the objectives. So the device that we used for this research is Ziffer by Harness, which is a chest-based wearable device. It's been proven reliable in previous studies for measuring various physiological metrics in construction workers. A limited research was done on it in the construction industry as well, and they used this device, and it was helpful, and the accuracy was satisfactory. So the device features an adjustable strap equipped with skin conductive electrodes to capture ECG signals and a pressure sensor that measures the breathing rate. Also, it has a 3-axis accelerometer sensor that records body acceleration and posture. And all these data is processed by a microprocessor in the device. And one interesting feature of the Zephyr by harness is that it can record up to 36 hours of physiological data. And the recorded data can be transferred to a computer using Omnisense software. Also, you can transmit this data in a real time to a laptop while the workers are working. This device is originally was designed for sports science, for the leaders in order to monitor the people in the ground. But we are applying the same concept in construction site, as a supervisor can supervise the construction workers and their physiological status while they're in the construction field. So the metrics that this device can record is heart rate, breathing rate, acceleration, and posture, as you can see here in this picture. This device can also estimate core body temperature based on these metrics, but we did not use that metric because we didn't want to rely on the estimation. Since we are doing prediction analysis, we went directly with heart rate, breathing rate, acceleration, posture. There are two other important metrics that this device can calculate. One of them is impulse load, which is a cumulative measurement of mechanical load. This is calculated by summing up the areas under the accelerometer magnitude curve, meaning that at the beginning of the workday, the value is 0. As the acceleration goes on, it adds up till the end of the workday. And the next day, it goes back to 0, and it measures the mechanical load, or the total summation of acceleration, the area under the accelerometer in a given moment. And another important metric that this device calculates is heart rate confidence, which is the signal to noise ratio. So based on the guideline that came with the device, the noisy data can be removed. We had like less than 5% noise. And one other thing, the time resolution of the data is 1 second. So each second, for each second, we have these metrics towards the working days. So to give you a background about the case study that we did, the case study involved bridge maintenance workers performing various construction activities. 5 maintenance workers volunteered and provided their consent for data collection. The experiment took place over 4 consecutive days in September 2022, running from 8 a.m. to 5 p.m. each day with a break for lunch. We recorded the data during the whole period, including the lunch break. And during this period, we continuously recorded the physiological data, including heart rate, breathing rate, body movement, acceleration, and body posture using the PSM device. To ensure data integrity and confidentiality, we just assigned a number to each of the workers and their devices. We did not get any other identification from the workers, and we used that same number in order to track the devices and the recorded data. At the end of each day, the collected data was transferred to a computer and organized based on the assigned number. Also, we did IRB for this project. This study protocol was reviewed and approved by Colorado Institutional Review Board. Our volunteers fully participated through the study and had the option to discontinue their participation at any time. So these are the steps that for the development of the research. You can see, you can see data collection, data preprocessing, feature analysis, heart rate forecasting models, and predictive analysis, predicting performance evaluation. So for the data collection, it was just collecting the data during the study period. And after that, we did data pre-processing, where I'm going to dive into it in the later slides. And then we did a feature analysis in order to figure out which of these metrics, collected metrics, has the most effect on heart rate. And then we did heart rate forecasting models, and then predictive performance evaluation. Let me go to the next slide. So data preprocessing, first a concatenation of the collected data, meaning that based on the numbers, we merge the data for each of the workers. And then data cleaning. So again, I mentioned noisy data and the confidence that's calculated by the device. Based on the confidence, we removed the uncertain data, and when we remove the noise, there is like some missing values. So in the next step, we did imputation of the missing values based on the consecutive values. We did average of the one-time stamp before and after in order to replace the noisy data. It was less than 5% toward the whole study. And then data resolution processing, and then creation of training and testing data sets for the machine learning purpose, and then data standardization, which is also a step necessary for machine learning models. So in our physical demand analysis, we use something called heart rate reserve, which is a metric that reflects the physical demand in the literature. It's widely used in the literature. So this heart rate reserve is calculated based on heart rate at a given moment. You can see in this formula here, heart rate at rest, which reflects the minimum heart rate, and then heart rate, maximum heart rate minus divided by maximum heart rate minus heart rate at rest. So this maximum heart rate can be calculated in two different ways. Once we can have the participants to run on a treadmill and they record the highest heart rate that they have and consider that as our maximum heart rate. We didn't do this approach because it was not feasible. So another approach that is also widely used in the literature is estimation of maximum heart rate, which is based on this formula, which is 208 minus 70% of the age. So based on this, you can calculate the heart rate max, and then this is the span of heart rate. I mean, it's a ratio between where we are standing compared to the rest mode and maximum heart rate compared to the rest mode. So this, because different individuals might have different heart rate, so this metric can standardize it. And so you can compare heart rate of different individuals in terms of physical demand with each other. That's why we use this measure. So, and also Norton et al., they have recommended some heart rate zones, and there's a description for each of the heart rate zones, and there's some suggestion for each of these heart rate zones. For instance, for sedentary, you can see 0 to 20% heart rate range. For light activities that require 20% to 40%, moderate 40% to 60%, vigorous 60% to 85%, and high 85 to 100. And then you can see for each of them, there is a description, activities that have little movement with low energy requirement. And then for moderate, let's say, and activities that can be conducted while maintaining a conversation uninterrupted. High activities that have a very high energy requirement. And then there's suggestions for each of these heart rate zones. For sedentary and light, you can see an intensity that can be sustained over 60 minutes. For moderate, heart rate 40% to 60%, remember this, we're going to go back to it, an intensity that may last 30 minutes to 60 minutes, not more than that. Vigorous, an intensity that may last up to 30 minutes, not more than 30 minutes in the vigorous heart rate zone. High, an intensity that generally cannot be maintained longer than 10 minutes. So based on these this heart rate zones, we did an analysis on our collected data, and you can see for each of the participants, 1 to 5, and for each working day, you can see the percentage of the heart rate zone in which they were in each day: sedentary, light, moderate, and vigorous. Firstly, we observed that the majority of the participants had multiple occurrences where their heart rate reserve exceeded 40% and was sustained over 60 minutes. So it's against the recommendation. This can be regarded as excessive cardiovascular overload. Interestingly, when we look at the cumulative time spent in high heart rate zone, which is indicated by red, it was generally low. However, there was an exception with the participant 4, you can see here, on day 4 that had a spike. Our data revealed that some participants experienced extensive cardiovascular overload. This highlights critical need for interventions to balance workloads and prevent such an overload. So you can see overall, based on this table, our workers are experiencing a cardiovascular overload. So we did we pictured the workers when they were working with timestamp. So we collected the timestamp photos, and we matched these photos with the recorded heart rate. This is heart rate reserve, by the way. So these are normalized, so we can compare them together. So you can see for jackhammer operation, you can see a spike here, and we have the time exactly, and you can look at the graph and see what was the heart rate in that. So we had this timestamp photos there on the job site, and we matched the heart rates and the construction activity to figure out which construction activities are more physically demanding. And based on our observations, concrete demolishing and jackhammer operations were the most physically demanding tasks. Then we did a correlation analysis between the features that we collected, including heart rate, breathing rate, acceleration, peak acceleration, posture, and impulse load. So this is a correlation. So the correlation of heart rate and heart rate are 1. So you can see this is all 1. We have 2 other metrics, acceleration and peak acceleration, that this peak acceleration is the maximum acceleration recorded in a 1-minute span. And the reason that we did this, you'll see in the future slides. But in short, it's more beneficial for our machine learning purpose if we consider peak acceleration. So you can see these two make sense that they have a high correlation. So only one of these should be selected for machine learning purpose to reduce the collinearity. And you can see on this column, you can see peak acceleration, and posture had highest linear correlation with heart rate. So let me go to the next slide. So right now in this slide, there's the difference between this. This is slide and former slide. This is time lag values of each of these metrics, meaning that heart rate at time 1 minute minus 1 minute. So let's say if the current heart rate is at time t, time t minus 1 minute, the heart rate value that was recorded, time minus 2 minutes, the heart rate that was recorded. These are the correlation between these metrics for each of the timestamp values with the heart rate at time t. So this is heart rate at time minus t correlation with heart rate at time t. This is for instance, for this one, this is acceleration. The value is 0.54 acceleration recorded in time t minus 2. The correlation of that value and heart rate at time t. So we want to see the time the time lag values of our metrics, how much they can predict or influence the heart rate at time t. So based on this is a linear correlation using Pearson correlation. We can see so heart rate values, time-like values of heart rate have a high correlation with heart rate. Acceleration and also time, this is time-like values of acceleration. They have high correlation, linear correlation, Pearson correlation with heart rate. Similar, same thing for peak acceleration, for posture, but for impulse load, you can see there is, and breathing rate, there is no linear correlation between the time-like values and heart rate. Please pay attention that this is only linear. So in order to, this only shows the linear, evaluates the linear correlations. In order to figure out whether there is like a nonlinear influence or correlation between these time-like values and the features and heart rate, we ran another analysis using k-nearest neighbors mutual information. So mutual information represents the amount of information that one feature can provide about the target value and is measured in bits unit of information. And then the calculated MI values were normalized by entropy of the heart rate, which is also in units of beats, to quantify how much a known feature can reduce the uncertainty in heart rate prediction. Results of mutual information analysis confirmed Pearson correlation results about time-like heart rate values. You can see for specifically for heart rate, acceleration, peak acceleration, posture, we have similar results. And also for breathing rate, it confirms the results of Pearson correlation. But there is a difference for impulse load. You can see impulse load didn't have any linear correlation, but mutual information analysis suggests that there is a high influence for, it's a nonlinear influence between impulse load and heart rate values. And then, so based on this feature analysis that we did, we developed 7 deep learning models to forecast the 1 minute ahead heart rate prediction based on time-like physiological activity-related metrics, such as body posture and acceleration. Features that were used in order to predict the heart rate was peak acceleration, posture, and impulse load. Models were trained using 80% of the collected data and were tested using 20% of the remaining data. So the models that we developed were convolutional neural network, a long short-term memory, LSTM, and this is hybrid model, convolutional neural network, long short-term memory, and then bidirectional LSTM or long short-term memory, gated recurrent unit or GRU, and CNN GRU, which is a combination of convolutional neural network and gated recurrent unit, and then bidirectional gated recurrent unit. So these were 7 different machine learning methods that we used. And please pay attention that these, for each of the construction workers, we tested these models. So there were like 5 construction workers, 7 different methods that were tried, 35 total machine learning models that were developed and evaluated. So you can see the results of these. So these are for the participants. For each of the participants, we developed these models and tested them. So the metrics that we used for testing these models were mean average error, root mean squared error, and mean absolute percentage error. These are 3 common metrics used in data science to evaluate the machine learning models. And based on the results that we got, although the results are not consistent and there might be some differences between different participants, but you can see long short-term memory or LSTM had the best overall performance. And here you can see the predicted values versus the true values. True values are shown by the color blue, and the predicted values for LSTM is orange, by LSTM is green, and GRU is red. So you can see the accuracy of the model in prediction. And these are, again, for the top three methods that we used for LSTM, by LSTM, and GRU, and only for participant 1 and 2. So this is participant 1 and participant 2. And in conclusion, results show physical demand can be highly variable depending on construction activity. Concrete demolishing and jackhammer operation resulted in highest heart rate levels and average daily heart rate. Time lag variables including acceleration of body movements, body posture, and impulse load have significant effect on heart rate. Long short-term memory network, or LSTM, had the best overall performance in heart rate prediction. Real-time forecasting of heart rate during workers' ongoing work can alert workers or supervisors if accepted heart rate thresholds are about to be exceeded. This system can be used to provide a flexible work-rest schedule with short breaks to avoid cardiovascular overload due to consistent high physical demand in construction work. And the results of the study could have broader applications in the field, such as heart rate attack warning systems and early fatigue detection. One other thing is that in the literature, there are some studies that have been conducted on correlating the heart rate or developing machine learning models that can predict predict fatigue based on heart rate. So if this model is used in conjunction with those models, you can predict fatigue in advance as well. So that's a future path for this research to predict fatigue in advance in construction workers. And all right, that's the presentation. That was for my side. If you have any questions, I'm more than happy to answer them. I think I finished on time. 30 minutes.
So any questions from the audience? I know Dr. Ghafouri went into some technical details there, but it was a very exciting collaboration on actually documenting applied construction work and data science, and look to see what applications we can use from that sort of machine learning techniques to predict worker, in this case, heart rate, and as Dr. Ghafouri said, in the future, potentially fatigue.
So I have a couple, and that is with the studies that you did, or with the subjects that you tested, was that contractor interested in maintaining that for the rest of the construction season, or did they just use it for a short period and then turn it back in and no longer had an interest? So what did they keep it, and what is their interest moving forward?
I can answer that question and put it a little bit in context. First of all, the bridge project itself was a very short project. These are maintenance teams. They come in, they do work. So we worked on a project that was complete, and then they were moving on to other projects. In general, contractors, this was, the city and county of Denver allowed us to have volunteers from their workforce. In general, contractors have been a bit hesitant to use our technology because they are worried that if they find something that's problematic, they might be sued. So we have to overcome the challenge in construction safety of too much knowledge versus not enough knowledge. And I think we're right at that boundary. In the future, once we show that these clearly established predictive safety indicators so that we can prevent accidents, everybody will be on board. But right now, it's almost that we reveal that the situation's problematic. and contractors aren't that interested. So we're right at that point with the research.
Okay. And then there's a question in the chat, and that is everybody's addiction to caffeine. So was the worker's heart rate impacted by caffeine? Was that a measure? And I think they're referring to participant number 4 when they hit that red zone. Would be my guess, because I wondered the same thing. Like, why did he hit red?
That was we did not explicitly like look for the caffeine intake, but they took Red Bull on one day. It didn't change the heart rate results that much, but it significantly the heart rate significantly varies by the activity that they do. And for instance, you can see on the day 4th day that happened, you can see this is spike here, and they were like trying to adjust this the bridge joint. So you can see, or here on the 3rd day, you can see there is one spike here, and when they were moving this joint to place it. So we observed that, you know, these are exactly these photos are timestamped, and we matched them with the heart rate that we recorded. So it shows, you know, the dangerous the thing that we care about is not to exceed the heart rate zones or stay in a red heart rate zone for a long time. So you can see here, you can visually check, okay, they were doing this, and look at the heart rate, what happened. So it shows that, okay, when there should be a break right after this, or when you're doing this movement, there should be before this. So it shows that how much it is important to have this, and usually this is not recorded. Nobody sees what happened for that poor worker. You know, they were moving in, and there's no documentation of it. So, I mean, when you look at what happened and the results that we have, and like match them, you can see the importance of this monitoring. And my proposition is that in the future, I mean, like if you have like sports players, you know, the supervisor can see, okay, what their workers are doing heart rate wise. You know, where they're standing. Are they too tired right now or not? Yeah, and it can help and benefit work rest schedule significantly. So I mean, like, you know, that, okay, how to at least plan the activities that are more intense, how to have the breaks over the work time. As we can see here, we have like a significant drop here during the lunch break from 2 to 15, and it's consistent over the 4 days. So you can see heart rate and activity are hand in hand.
That was that looks like the smart one. He looks like the one who took a nap during lunch.
Well, it's interesting. The workers, we showed them the results, and they, of course, were trying to figure out who was who. Now, I will add to Madi's comments and get back to the caffeine question. There were noticeable, and he talked about impulse load. Truly, the spikes in heart rate were mostly to lifting. So if you look at, they were trying to use a crowbar and really exerting themselves to put that expansion joint in place. And the other time was when they were lifting the very heavy. So it was, if I think about it from a non-medical point of view, the spikes that we were seeing in the high exertion were really from a critical quick lift or a critical use of a crowbar. As for caffeine, the very interesting thing in some of the studies that preceded this, we had a lot of questions on people, you know, what was their sleep the night before? What had they eaten for breakfast? Did they have caffeine? We cannot control for that. And, or we have not been able to control for that, especially with actual workers. What we did do, some of these monitoring systems do account theoretically for age and weight. And so there is some information that we do customize the monitors for. That being said, there's a lot more work to be done in this. And absolutely, it's almost a sort of a culture to drink Red Bull right when you go on or right at lunchtime. Joking aside, these are impacting factors, and we cannot fully control for them yet. Other things, ambient temperature. There are a lot of variables on construction sites when we're actually talking about physical stress loads on the body. And this is why it's a rich field for research and why this is just a starting point of looking at, can these methods be applied in this kind of situation?
Yeah, then the follow-up question was on that one was, do you have any plans in the future for additional study on heart rates and how it's impacted by hydration levels? That was going to be my other comment was, and Caroline, I'm glad you mentioned, the sleep and the nutrition side, because obviously that plays a huge factor in heart rates. So hydration level, caffeine consumption, the temperatures, the ambient air, and then the recreational drug use. Are you planning on doing some additional research in this area and like trying to factor in some of those items?
We would certainly like to, and there are some other colleagues who, at other universities who are doing some heart rate testing. And we, right now, do not have any active projects, but again, we see it as a ripe opportunity for more research.
I think,
Absolutely.
and seeing this, nothing really plateaued and peaked for a long period of time. So you do see the ups and downs, which I think is to be expected. But when they're under heavy stress, thankfully that heavy stress was a short period of time, so it wasn't long durations. But still, as managers, peers, supervisors, colleagues, whatever, we all need to be aware of that and make sure that we are providing those opportunities for our peers to, even ourselves, that if we need to take that break, take that break. And so I think this is really good data to share. So thank you for that. But Madi, go ahead. Sorry.
Yes, absolutely. There is one important thing to consider when you're talking about different factors, and they're considering different factors while you are collecting data. So one huge obstacle, I think, in this research is data privacy. We are not allowed to collect data. Every data that we are collecting from the workers should be justifiable, and also the participation is voluntarily. Yeah. So we cannot if you are asking for too much, or what did you eat? Did you drink coffee or not? That can we want our participants to continue collaborating. So there is another challenge, and also data privacy. Even if the contractor or the supervisor is collecting this data, so we de-identified the data, so we didn't know who's who. We just had numbers. But so what if there was some heart problem that they observed? That person can lose their job. Or what if you can use their heart rate as a measure of productivity and push them to work harder. There should be some regulations in order to make this application of this technology. Definitely there should be some regulations and to make the application feasible. And I think in the future these obstacles and more research should be done, especially on the privacy part and regulatory part. To make the usage of such a technology feasible for contractors and ensure the data private. So because if the workers feel that their data might jeopardize their position, so they might not continue, they might not want to participate at all, even in real time, in a real situation. Yeah.
I love this research. I'll just throw that out there. I think it's really important information to know, and I'm glad you guys did this because I think it is something we need to be more aware of. And I would absolutely love to keep the anonymity of heart rate monitors, and for contractors or even even the DOTs possibly to potentially manage, so they can keep an eye on it. I will say, from not my own personal experience, but my firsthand experience with others, we have heart rate monitors, chest straps that we use at my little side gig that I do. And what we found with that was we had one individual that would fatigue out really, really quick. And so when we started looking at his data on his heart rate monitor, he shared it. We visited with him about it. And we found he actually was having some heart issues. And so he went in and I always say they rebooted him. But they found he was actually in AFib, and so they were able to go in and correct it and address it. And he argues that we saved his life because we started monitoring his heart rate. So that is the potential here of a benefit and an outcome. Is rather than looking at contractor may not want to do it because they may feel like they're obligated for something, and or if I'm wearing it and I have really bad heart rhythms and I find I'm peaked and everybody else is down here, then they may let me go because they're like, you're not fit for this for duty. But I think it's a really good monitoring thing too, just on the health and welfare and well-being of our coworkers, just to make sure everybody is obviously healthy and safe. And if not, we address it and we put them in appropriate positions.
Chris,
So
thank you.
Yeah,
Look,
I would love
I will
to
just
see.
say, oh, go ahead.
I was going to say, I would love to see them continuing using this and seeing it evolve. So
Well, one of the things, and Madi, it sounds like you have a comment too. At first, when we did this, because the accuracy drops precipitously after, so we were really doing a 1 minute look ahead. And if you do a longer look ahead, the accuracy does fall off. And at first I thought, well, how useful is that, a 1 minute look ahead? And then I realized 1 minute is a long time. If you are saving somebody from, if you were saying, nope, stop what you're doing, you're getting into trouble, a minute prediction, and we don't know, but if these algorithms prove rich and we gather more data and we know what the variables are, we might extend that look ahead time for accuracy. But just even telling somebody, hey, time to take a break, I think so if somebody were alerted or self-alerted that you're reaching your maximum heart rate, go get a sip of water, I think it could really make an impact on the safety of construction sites. And particularly, we usually get this question, particularly as the world is getting hotter and we are doing construction out in more exposed, hotter climates. I think this kind of prediction is going to serve the construction community very well.
Absolutely. Heart rate monitoring, mainly, I think the most important part of it is to make sure that two things. First, they are not exceeding the time that they spend in heart rate in a dangerous heart rate zones. Make sure that they have breaks at the appropriate times. And also the second thing that is that, for instance, when this spike happens, okay, hold on, you can control what's happening, and that prediction can help. Also, as you mentioned, for fatigue detection, we don't need that much. So these are the actual heart rate. I mean, like the predictions that we have here. Let me show that one. These are the actual heart rates, and you can see. I mean, these are not normalized or anything. You can see. So it is very important when you're for heart attack warning system. It's very important to estimate the exact heart rate. So the accuracy is very important. But when it comes to fatigue detection, you don't need that accuracy that much. So for the fatigue detection systems, there can be future research for this. I mean, as a continuous of this research, so you don't need I don't know, to the person accuracy. So, you can do longer spans, advanced predictions, and then based on that, you can predict fatigue, for instance. You know that, okay, they're going to be tired in 10 minutes or 15 minutes. So right now is a good time for a break.
Well, not seeing or hearing any other questions, we certainly appreciate your guys' time to share this research, and thank you for doing the research too. I think this is fantastic, and I would argue out of the box, that's something that isn't expected of maybe some researchers, and I love that you're looking at this because this is critical to our success of our infrastructure as we advance it and move it forward. Thank you everybody for attending today's event. We certainly appreciate your time and attention. We hope that you enjoyed and gained some new knowledge from today's session. Be sure to bookmark our website at translearning.org for upcoming presentations. We're getting ready to start our new TLN season in October. So that website will be getting populated here real quick. But you will also be able to access the learning management system, and then you can also navigate to the CTIPS website where you will find the recording from today's presentation along with the documents for the research. So if you are interested in that, again, go to our website where you will find it. With that being said, have a fantastic rest of your week. It is Friday, Junior, so if you are working tomorrow, have a fantastic rest of your week. Be safe, and don't forget to be awesome, everyone. Take care.